Welcome to another explainer. Today, we're getting into the heavy-duty engineering that makes massive underground structures possible. We're talking diaphragm wall construction. Have you ever stood in a deep underground metro station and wondered how on earth did they carve out this massive cavern without the entire city above it just caving in? Well, we're going to figure that out today.
Let's start with a big problem here. When you dig deep trenches in soil, especially if you're dealing with high water tables or loose ground, the earth naturally wants to cave inward. You've got gravity and hydrostatic pressure constantly fighting against your excavation. If you just dug a giant hole, the surrounding buildings and roads would literally slide right in and join you at the bottom.
So here's our blueprint for today. 1. What are diaphragm walls? 2. Step 1. Guide walls. 3. Excavation and bentonite slurry. And 4. Reinforcement and Tremie concreting.
Number 1. What exactly are diaphragm walls?
The ultimate solution to this deep excavation problem is the diaphragm wall, or sometimes you'll hear it called a slurry wall. It's actually wild to think about, but instead of digging a giant open hole, engineers build a continuous reinforced concrete wall directly into the ground before the main excavation even happens. These serve a totally critical dual purpose. They act as a retaining structure to hold the earth back and as a deep foundation. This is the exact tech used to build massive projects like the Lucknow Metro, major dams, and high-rises with crazy deep basements.
Just look at the sheer size of this specialized rig. Diaphragm walls are basically rectangular section excavations carved out of the earth in individual panels. To slice through tens of meters of solid earth and rock, you need an absolutely unfathomable amount of weight and mechanical force. We're talking towering cranes and heavy-duty mechanical rigs brought in just to manage these incredible stresses.
Number 2, Step 1, the guide walls.
So, before any heavy digging actually starts, crews have to identify any underground utilities, pipes, wires, and totally clear the area. Then, surveyors map out the exact center lines. The crews do a pre-trench excavation, either manually or with small excavators, going down just about 1.5 meters. Inside this super shallow, highly precise trench, they lay down the initial concrete forms.
Notice the inverted L shape of these reinforced concrete walls. These guide walls are absolutely crucial. They basically serve 3 main purposes. First, they protect the fragile upper edge of the trench from completely collapsing under the massive weight of those rigs we just saw. Second, they provide a permanent, perfectly aligned track for the digging equipment to follow. Think of them as a rigid physical template that ensures the wall goes down perfectly straight.
Moving on to number 3, excavation and bentonite slurry.
Plunging right between those concrete guide walls is the main digging tool, which is usually this massive mechanical or hydraulic grab. This tool is precisely sized to match the exact width and length of the rectangular panel they're digging. It drops down, its jaws bite into the earth, and it pulls the soil out, safely discharging it up on the surface. And it just repeats this cycle, biting deeper and deeper into the ground, sometimes reaching depths of 50 to 100 meters.
But hold on a second. As that grab digs a 100-meter deep, narrow slit into the earth, why doesn't the trench instantly collapse inward from all that pressure from the surrounding soil and groundwater? Well, this is where the chemistry comes in. Engineers constantly pump a fluid called bentonite slurry into the hole as they dig. Bentonite is basically weathered volcanic ash, packed with a fascinating clay mineral called montmorillonite. Mix it with water, and it swells up to create this thick, highly viscous suspension.
The really crucial point here is that this bentonite acts like a kind of liquid scaffolding. Because of its unique viscosity and density, it uses hydrostatic pressure to push outward against the soil, completely counteracting those inward forces of the earth and groundwater. It literally holds the trench walls open without a single piece of solid bracing. Plus, it forms a protective filter cake right along the walls of the trench and suspends the loose soil cuttings so the grab can easily pull them out.
Because this slurry is so incredibly vital to keeping the whole operation from collapsing, the job site basically turns into a massive plumbing system. If you look closely here, you'll see the trench is hooked up to an entire specialized plant dedicated to producing the slurry, pumping it in, and pulling it back out to run through a desanding unit. The fluid has to be constantly cleaned and refreshed so its density, viscosity, and pH levels stay perfectly within the spec limits.
Okay, so we know how a single deep trench is dug, but we're building a continuous wall here. To do that, engineers use a really clever skip-a-space rhythm. They don't just dig a trench from point A to point B in one straight shot. Instead, they dig and construct primary panels with gaps left between them. It's kind of like filling in the black squares of a chessboard first and then coming back later for the white ones. Once those primary panels are done and the concrete sets, that massive grab returns to dig out the secondary panels in the empty spaces.
And to make sure this alternating sequence actually functions as a secure wall, it requires highly specialized waterproof joints between the panels. For instance, they might use something called a Milan joint. Remember, one of the main jobs of a diaphragm wall is to keep groundwater out. So as the secondary panels are poured between the primary ones, these joints ensure the entire perimeter links up into one continuous, leak-proof barrier.
And finally, number 4, reinforcement and Tremie concreting.
First up, we need structural strength. Once the bottom of the excavated panel is totally clean, a service crane hoists up a massive prefabricated steel reinforcement cage. These cages are incredibly heavy and super long, so they're usually assembled flat on the ground nearby. Just imagine the sheer scale and tension of hoisting a multi-ton steel skeleton into the air and then carefully lowering it directly into a deep pit filled with volcanic ash mud. It's a seriously stunning display of precision.
Now we face a pretty unique concreting problem. In standard, everyday construction, you pour your concrete into empty wooden or steel forms filled with nothing but air. But here, we have to use the wet method. We need to pump wet concrete into a trench that is already filled to the brim with wet bentonite slurry. So how do we safely displace that support fluid without mixing the two together and totally ruining the structural integrity of the concrete?
To pull off this fluid displacement magic, engineers use a tool called a Tremie. It's basically a vertical steel pipe with an open top. Notice the funnel shape right at the top of the pipe. That gets lowered to the very center of the steel reinforcement cage all the way down to the absolute bottom of the deep trench.
The mechanics here are elegantly simple but brilliantly effective. The heavy concrete is pumped down through the Tremie, which means the trench starts filling from the bottom up. Because the concrete is significantly heavier and denser than the bentonite slurry, it stays at the bottom and smoothly pushes the lighter bentonite right up toward the surface. As the concrete level rises, the Tremie pipe is lifted progressively higher, always making sure its nozzle stays buried in the fresh concrete. The bentonite slurry just gets pushed right out the top of the trench, where it's collected, piped back to the desanding plant, and recycled for the next panel.
And there you have it. It's this perfect, highly orchestrated marriage of heavy excavation machinery, those massive rig grabs, and the complex fluid mechanics of bentonite slurry that makes modern subterranean architecture possible. Without this method, the massive high-rises and transit systems of modern, crowded cities simply could not be built safely.
I really hope this explainer changes how you look at the deep infrastructure hidden right beneath our feet. Thanks for exploring this with me today. Now, the next time you're traveling down a long escalator into a massive, deep underground station, take a look around and ask yourself, what unseen liquid scaffolding made this space possible?